So in the previous lecture, we discussed about different eutectic transformations which can be takes place in case of phase diagrams. So in today's lecture, we'll discuss one more important topic related to the solidification process of a alloys, particularly in casting alloys, that is coring. And this coring, what is mean by coring and why coring comes into picture. So in order to understand the effect, what is mean by coring, we will discuss copper nickel system. So as you can see, this is a equilibrium diagram of a copper nickel system. So you can see, so this line we call is a liquidus line and this line we call solidus line. As we know, by construction of the phase diagrams, we discuss this topic. The region above which everything is in liquid we call liquidus line, and the region or the line below which everything is in solid phase we call solidus line. In order to understand this coring phenomena, let us consider this 35 weight% nickel alloy. So 35 weight% nickel alloy. So initially we are at 35. If you heat this alloy around 1300 degrees centigrade, you can see everything is in liquid. So state is liquid and composition of this liquid is 35 weight% nickel. Now if you cool it slowly, then exactly at B dash we can find out composition of liquid and composition of solid by using tie line. And if you draw tie line exactly here, composition of solid is 46 weight% nickel. You can see 46 weight% nickel is the composition of solid, which is nucleated in the liquid phase, and the composition of liquid, that is same, it becomes 35. So slowly if you go down, the composition of liquid is varying along this line and composition of solid varies along this line. So it means composition of liquid varies along liquidus line and composition of solid varies along solidus line when you follow equilibrium path. So equilibrium path means it's a very slow coring. But in most of the casting industries, if you follow equilibrium cooling, it will take days to go for a casting and production rate will not increase. So it's not economical. So equilibrium process is not economical way. So we'll go non-equilibrium way because that is faster. So metals can solidify very fastly. We can produce more castings in a single day. So non-equilibrium way is the preferred method in casting industries. So what is that non-equilibrium way? So cooling rate in non-equilibrium way is higher than the equilibrium way. So means we are allowed to cool all the molten metal into the air, into the forced air, so that it will cool fast. So whenever you are disturbing the equilibrium path or equilibrium cooling rate, means you are not following equilibrium diagram. So you will not get the phases or you will not get the composition matches with the equilibrium compositions. Also you will not get the states or phases present in the equilibrium in actual condition. So means there is a difference in equilibrium cooling and non-equilibrium cooling. So non-equilibrium cooling is faster than the equilibrium cooling. So what happens due to this non-equilibrium cooling? Suppose from this point B dash you have started in non-equilibrium cooling, our cooling rate is very faster. In that case, you are deviating from this solidus line. You can see it here. So you are deviating from this solidus line. So this dash line indicates, so this solidus line is tilted in this equilibrium cooled environment. And these are the new compositions. When you follow this path, you can see 46 weight percent nickel at this point. Then at point C dash, composition of liquid is 29, but composition of solid here in non-equilibrium it becomes 42. It should be 40. So when you find out this composition at this point, you will get 40% nickel, that is composition of solid. Then at this point, you should have 38 weight percent nickel, but you will get 35 weight percent nickel. At this point, completely you have solid phase as far as the phase diagram is concerned, but you are following non-equilibrium path. You can see still liquid is present at point E dash. You can see it here. So means at this point, so this is the microstructure, or some solid is nucleated into the liquid and the composition of solid is 46. But from this point onwards, you have started non-equilibrium way. So what happens? You are at this point now. You can see this is the state microstructure of this point, C dash point. So liquid composition is 29 and solid composition is 40 weight percent nickel. So initially we had 46 alpha composition 46, you can see. Next you will get alpha 40, next you will get alpha 35, and next you will get alpha 31. So solid composition is changing from center to surface. You can see the composition of alpha is varying from center to surface. At the center we have 46, then 40, then 35, then 31. So composition of solid is a continuously changes. So as point changes, as location changes, the composition of your alloy is also changing. So this is not a homogeneous alloy, this is a heterogeneous alloy. And this is what we call as a coring. This is what we call as a coring. There is a chemical ingredient exists within this alloy. And a chemical ingredient, you can see from center to surface, you have different chemical composition. At the same time, why you have obtained this different chemical composition? Because you have gone to non-equilibrium cooling. You can see at this point, as far as our equilibrium diagram is concerned, at this point, as far as the equilibrium diagram is concerned, below that you should not have any liquid phase. But you can see it here. Still we have one liquid, and liquid composition is 24. At point E dash, as far as our phase diagram is concerned, we have all solid, but you can see it here, still liquid exists. So means it is due to non-equilibrium cooling. You have deviated from the solidus line, the small tilt in the solidus line, and that's why you have obtained different chemical compositions of the solid. And this different chemical composition, it is due to different chemical composition of the solid. The chemical ingredient exists in the system, and this chemical ingredient is nothing but coring. And this coring has to be avoided. It is a very dangerous thing. It has to be avoided because the coring directly, obviously microstructure changes, mechanical property changes, as we know that. So due to coring, you will not get uniform microstructure, and due to that, the mechanical properties considerably affect. Also, corrosion properties considerably will affect. So coring has to be avoided. So how to? But we don't have any other option. If you go for equilibrium cooling, it will take some time for solidification, and you will not, and that is also not economical. So industrial practice is to go for high cooling non-equilibrium way. So what we do after solidification, we know that it is a cold structure. So what we do after solidification, we just heat this alloy just below solidus temperature. So solidus temperature means, so this is solidus line, so just below solidus line means somewhere here at point E dash, around 600, around 800, 900 degrees centigrade we will heat here. So the temperature in degree centigrade, so this is 1100, So maybe in between 1100, 1200, somewhere here, 1180 degrees centigrade, we will heat this alloy and we will hold it there. We will heat this alloy at this particular temperature and we will hold it there. So what happens here? So at this point, we'll hold the alloy for a long time. So this is our heat treatment cycle. So from 35 weight percent nickel, we will heat this alloy. So you can see it here. So after coring, we know that it is a heterogeneous uh, structure now, because chemical composition is changes as the point changes. So what we do, we have to heat this alloy just below solidus temperature line, so somewhere here, and we will hold it there for some time. So we'll hold it there for some time here. Sorry. We'll hold it there for some time. Then again we will cool in the air. So like that. So let us heat this alloy. So our heat treatment cycle becomes in like this, in this way. So this is our temperature line, for example, around 1000, around 1100 or something like that. So we'll heat this alloy just below solidus temperature line for prolonged time. Then we will cool in the air. So this holding is very, very important. So this, why this holding is important? Because what happens here, due to this holding, so all these solid phases composition ranges from 46 to 31. So distribution of atoms will start. So diffusion of solid atoms will start, and due to this diffusion of solid atoms, homogeneous solid phase will get. Because initially why we obtain or why we get heterogeneous solid phase, it is due to non-equilibrium way. Means cooling rate was very fast. We have not allowed any time for diffusion of the solute atoms. We have freezed the solute atoms. So that's why cooling rate was very high. Cooling rate was very high. So that's why we have freezed the solute atoms. We have not allowed to grow. We have not allowed to properly distribute. If you allow that, then we should have obtained only one solid of uniform chemical composition. But due to non-equilibrium cooling, we are freezing continuously every phase of the solid phase, starting from 46 to 31. We are not allowed to grow it. And due to that, chemical ingredient exists. So what we do, we will heat this alloy below solidus temperature line for prolonged time. We will hold it there. So what happens during this holding process? So all the solid atoms will redistribute themselves, and due to this redistribution, you will get uniform alpha of chemical composition 35, and that is due to diffusion process. So that's why we call this treatment as homogenizing treatment. As homogenizing treatment. So this homogenizing treatment has to be performed. So that's why homogenizing treatments or heat treatments are generally recommended in casting processes. So cooling in a copper nickel binary system. Now this is by using equilibrium way. Let us understand what exactly happens in equilibrium way. So initially we have liquid of 35 weight percent nickel. If you cool it slowly, then we have 35 weight percent nickel, but at point B we also have solid having composition 46 weight percent nickel. Then at point C, 32 weight percent nickel is the liquid composition and 43 weight percent nickel is the solid composition. Now you can see it here. 46, 43, but we don't differentiate 46 separately and 43 separately because this is a equilibrium path we are following. So you will get only one phase, solid phase having same composition, that is 43. Then in the next case, composition of solid is 36, composition of liquid is 24. And finally at point E, we have all solid having 35 weight percent nickel. So this is by using equilibrium way you can obtain the this is the equilibrium path, cooling path in equilibrium way. So this is cold versus equilibrium phase. So C alpha changes as we solidify. So first alpha to solidify is 46 and last is 35. You can see. So it's a cold structure. Due to different chemical composition, you have obtained different layers of the solid. But when we perform homogenizing treatment, so after homogenizing treatment, you will get this uniform C alpha. Okay. So due to slow rate of cooling, you will get equilibrium structure. But again, if you want to perform homogenizing treatment, so after homogenizing treatment also, you will get this uniform C alpha. So this structure can be obtained after homogenizing. Okay. So the extent of pouring or degree of pouring increases with increasing separation between liquidus and solidus, that is alloys with wide freezing range. So difference between liquidus temperature and solidus temperature suppose increases, so the extent of pouring also increases. What is the difference between solidus temperature and liquidus temperature in case of eutectic alloys? 0, because eutectic alloy solidifies at one particular temperature. So there is no difference. So in case of eutectic alloys, theoretically you will not get coring. So that's why eutectic alloys are highly preferred in casting industries, because due to low melting point and as well as coring phenomena is absent. But if you are looking at off eutectic, liquid plus solid region exists there, in that case chances of corings are there, and this separation increases, you will get more pore structure.